Welcome to our Monday, April 8th remote lecture. Here on Canvas, I don't have this published yet, but it must be published now because you found this video. The office hours for Monday, April 8th are going to be remote as well. They're not going to be in person. And this is the link to my office hours. And then the lecture is not in the classroom. Hopefully you did not go there unnecessarily. It's this video. If you click on the Monday lecture video to get this video, this is where I will put this. And then in addition to this video, I'm going to make this shorter because then there's lots of material that I already have videos for. One of the topics that we need to cover is the 7.4 section 4 of chapter 7, and there's already a 31-minute video on that going through the note packet. So we'll let you take a look at that. And then also finishing up chapter 7, we're going to start chapter 9 as well. The beginning of chapter 9 is another video that's already posted going through the first 3 sections in the chapter on solutions, electrolytes, and solubility. So just going through the note packet, I already have a video for that. So this video I wanted to kind of point out what's on Canvas right now, looking towards our end game for finishing up the semester. In addition to this module with the lecture here in it, I put a module for this week, week 11. There are a couple of assignments that have to do with the video on the chapter 7, section 4 that we're looking at today in this video, and or the videos for today. And then also solution concentration is coming up as well. We'll be talking more about solution concentration on Wednesday in class, but I just wanted to point out that we have those assignments. We also have links to the videos for chapter 9. That's the M6 videos, are the videos for chapter 9. I just put an extra copy of that in the lecture video page just to focus everybody's attention on it. But all the videos for chapter 9 are here, and the filled in note packet is over here as well. And then I went ahead and posted the final 2 weeks modules, and also all the final homework assignments that are up there. We already have enough homework points, so any of these homework assignments that you do, first of all, are really good for practice, and second of all, will replace any of your low homework scores, or if you missed a homework, it will replace that score. So I do encourage you to keep doing the homework assignments. We have a couple, I think we have 5 homework assignments remaining in the semester. So we have 1, 2, 3, 4, and 5. So there are 5 final Canvas homework assignments that are posted. And then in addition to module 6, which is chapter 9, we also have some videos and some filled in note packet for chapters 10 and 11. We're going to do just a little bit of 11. After exam 5, we'll have a little bit of 10 and 11 that we are talking about as well. Exam 5 is coming up on Monday, April 22nd, and I have the information page for that posted already, and also some additional practice problems that have to do with chapter 9 solution chemistry that will be helpful for exam 5. Okay, so as we finish week 11, I will go ahead and move that down below, and then week 12 will be on top. So as we do each week, I'll be slightly rearranging the module order. But I'm not going to be posting too many more things to those modules. I do have one other module on the final exam. It has some practice Canvas assignments that you can go through unlimited attempts and see how you're doing with some of these review problems that I've posted. There's also a format of the final exam and some links to some fun videos. So there's another module here for you to look at and look for. And then this module has been here the whole time, but there's also extra practice files for chapter 9, 10, and 11 on here as well. So there's plenty of practice for you to do if you have the time. So instead of following the note packet, I wanted to just talk in general about what happens when things dissolve in water, because that's relevant for both what we're doing at the end of chapter 7 and the beginning of chapter 9. This is coming from the Libra text. This picture here, what page is it? It is from the 9.2 page, solids dissolved in water. There is a fun video on how to make rock candy, but I'm not going to play that one for you. We're just going to talk about what happens when you dissolve ionic compounds in water compared to covalent compounds. So here we have a little diagram of 2 electrodes in some water. This first beaker of water has ethanol dissolved in it. This one has potassium chloride, and this one has acetic acid. And so we have the light bulb not lighting up. The middle one has the light bulb lit up, and then this last one has a very faint or dim light bulb here. The solution's conducting electricity a little bit in this last beaker. It's conducting the electricity a lot in this middle beaker, and it's not conducting the electricity very well in this first beaker at all. So why is that? Let's take a look at the structures of ethanol, which is covalent, and this one is ionic potassium chloride, and this one is a weak acid. So I've drawn some of the structures on this page. This first structure here, way off to the left, is the structure of ethanol. It's a covalent molecule. And so these molecules of ethanol, when you put them in water, they separate from each other, but the carbons and hydrogens and oxygens do not fall apart. These covalent bonds are not broken when you dissolve the ethanol in water. They are still there. And so the ethanol molecules are floating around as separate molecules, but none of the molecules have a charge on them. That's what's being shown. These 2 little green dots, I guess, represent the 2 carbons in the ethanol molecule. There's no charges on any of them. Potassium chloride do not have a covalent bond. We do not draw a line between potassium and chloride when we draw the structure of potassium chloride. So potassium chloride is made up of potassium plus 1 ions, chloride minus 1 ions, and they are not, they don't come in pairs of 1 potassium to 1 chlorine. The potassium chloride formula, remember, for an ionic compound, the formula that you show is just the empirical formula, the simplest ratio of cations to anions that you have in the compound. And since potassium is plus 1 and chloride is minus 1, the ratio is 1 to 1. There's 1 potassium for every chloride. So we draw the formula as KCl. But really, the crystal of potassium chloride is a lot of potassium and chlorine packed together. I'll show you another diagram in just a moment. And when you put them into water, they all separate from each other. If you can see these photos, we have some negative ions traveling toward the positive plate, and we have some positive ions, the potassium traveling towards the negative plate, and they're all separate from each other. So the water dissolves the potassium and the chlorine separately because there is not a covalent bond between them. Dissolving something in water does not break covalent bonds, but there is not a covalent bond, so they can flow apart from each other. And here is just one diagram in the LibreText page that we saw earlier. This one is also showing an ionic compound dissolving in water. This one specifically potassium chloride. The hydrogen part of the water is surrounding the chloride. The oxygen part of the water molecules is surrounding the potassium. Here's a crystal that's in the process of dissolving. This part of the crystal is still together. It's not dissolved, and at the edges of the crystal, the water is starting to dissolve the crystal by surrounding each cation and anion as it comes off of the solid crystal structure. Then we have the special case of a weak acid. Most of the weak acid exists as a covalent molecule. I've drawn it for you over here. There are covalent bonds, and so these molecules are not broken up and they do not have a charge. These 2 little green balls stuck together represent the full molecule. No charge is written on there, and that is not conducting electricity. A small amount of the acetic acid can be thought of as existing as this hydrogen cation and the acetate anion. Remember, acetate is a possible anion here. It was one of our polyatomics that we learned, C2H3O2 with a -1 charge. All those C's, H's, and O's in the acetate ion are held together by covalent bonds, so these do not break apart in water. but when this is ionic and the hydrogen is ionic, then these pieces can separate from each other in the acetic acid. And so that is what's being shown here. We have some acetate ions, negative ions going towards the positive plate, and some hydrogen ions going towards the negative plate. So I found another picture of an ionic compound breaking apart in water, sort of showing how this happens and why this happens. So here we see the water molecule, H2O. The oxygen end of the water molecule is slightly negative, and the hydrogen end of the molecule is slightly positive because the oxygen-hydrogen bonds are extremely uneven. They're extremely polar. So these molecules have a positive end and a negative end. The oxygens surround the cations, the hydrogens surround the anions, and then one by one these ions are picked off of the structure. You can see here what I said, that there's not really a molecule, one positive and one negative ion together. The ionic crystal, the salt, is a collection of positives and negatives all stacked together in this grid. And so the formula is just the empirical formula. This is a one-to-one crystal that we see here. So this could be something like potassium chloride or sodium chloride, where there's one potassium for every one chloride, but no single potassium is bonded to a specific chloride. They're just all in alternating pattern, one-to-one throughout the crystal. So this diagram over here is one that I found where you have covalent molecules. This one you have carbon tetrachloride, CCl4, and the carbon and chlorine are bonded with covalent bonds that do not break when you dissolve them in water. And you put this into a solvent, it wouldn't really be very water soluble, but if you put this into a solvent that it dissolved in, the molecules would go apart from each other. So these ones would break, these interactions would break, but the covalent bonds between like the carbon and the chlorine would not break. So here's one last drawing that I found of the difference between ionic compounds, strong electrolytes that completely dissociate in water. So that includes ionic compounds, strong acids, and strong bases. They all completely ionize in water and completely dissociate. Weak acids and weak bases have some of the molecules together without a charge, overall zero charge, whereas they have some of the ions flying apart from each other, but very small amount. Whereas something like ethanol that we talked about before, something that's a covalent compound, a sugar molecule is another example. These do not separate in water because they're held together entirely by covalent bonds. There are no ions that are going to get surrounded by water. The water just surrounds the whole molecule, and the molecule stays together as a molecule. So this is what I was trying to show in the in-class assignment from last week, in-class assignment 19. We were just taking a look after the exam. I wanted to stay away from calculations, so we were just taking a look at these pictures of how things might look when they dissolve in water or not dissolve in water. Here, this first example, we just have NH3 as a liquid itself, so it's not mixing with anything. It's not mixing with water. It's just a liquid. So all these NH3 molecules are sitting in a beaker. It's a liquid, and the molecules themselves do not fall apart. They're just discrete molecules. They move around past each other because liquids have some motion. They're able to move and flow, but they're just all together. Carbon dioxide gas. I drew a little balloon with these gas molecules. I drew a little 3-dot thing to show the linear carbon dioxide molecule, and they're all floating apart from each other inside the balloon, but the carbons and the oxygens are not floating apart from each other. The molecules themselves are all intact, and then they zip past one another, not interacting very much if they're a gas. If something is a solid, here's an ionic solid, again, plus and minus ions alternating, all packed into a solid crystal structure that is in a dry beaker. If you add water to this beaker, and it's now an aqueous solution, so when you dissolve it, it becomes an aqueous solution. It's dissolved. Now we have the sodium cations and the chloride anions floating apart from each other, each of them surrounded by water molecules. So we have another example of that with some other ionic compounds, magnesium sulfate, which dissolves in water. So we have magnesium sulfate dissolved in water. The magnesium ions and the sulfate ions separate from each other, but the sulfate ion itself does not fall apart into sulfur and oxygen. The sulfate stays together because the sulfur and oxygen have covalent bonds that attach them together. So this large piece, it represents the SO4 with a -2 charge that's floating apart from magnesium. And then here is magnesium carbonate, another ionic compound. This one is not soluble in water. It's a solid that's just sitting at the bottom of a beaker. This one might not even have any water in the beaker, but even if it did have water in the beaker, it would not be dissolved. It would still be sitting as a solid at the bottom. And we have alternating positive and negative ions in that crystal. We have here an interesting example of hydrogen chloride. As a gas, the molecule would stay together as covalent molecules, and here we have each hydrogen chloride molecule. I drew a little strange design. It looks a little like a coffee bean, and they're floating around inside a balloon to show that they're a gas. Hydrogen chloride is a strong acid, so when it dissolves in water, it does dissociate and it breaks apart to make hydrogen plus ions and chloride minus ions. So this is pretty unusual. For our purposes, we have learned about hydrogen chloride being a covalent molecule. So I would warn you if there is a strong acid that you're expected to break apart in water like this. So just like I did here, I put a note that this is a strong acid, and so that would completely dissociate into positive and negative ions in water. So I've been talking a lot about how things dissolve in water and what that means, what happens when they dissolve in water. One of the things that we did with this from chapter 7 in section 4 was we were able to write the total ionic equation and net ionic equation for certain reactions that take place. And we're trying to accurately reflect what is happening when you dissolve it in water. Anything that is ionic, when it dissolves in water and you see that little AQ, that it's an aqueous solution, then it does dissociate into ions. The silver nitrate would dissociate and make silver ions as the cation, nitrate as the anion, and they would be floating apart from each other. So you would have aqueous silver ions, and separately from that we would have aqueous nitrate ions. So this ionic equation is trying to reflect reality. This is what it would actually look like. They'd be floating apart from each other. The same thing would happen with lithium bromide, which does dissolve. It's soluble, and when it is in aqueous solution, the lithium cations and the bromide anions are apart from each other. So we show them as separated and dissociated. Silver bromide is not water soluble, so we see that it's a solid sitting at the bottom of the beaker or test tube, and since it's sitting together, we're going to draw it together. We do not dissociate it because it's not aqueous. It's a solid, so it's not dissociated. The only thing that we're dissociating are things that are aqueous if they are ionic. Lithium nitrate is dissolved, so the lithium and the nitrate are floating around separately from each other. Once we have our total ionic equation, we can go ahead and cross out anything that is just a spectator. Anything that's just a spectator that's not changing very much, that it's the same on the left as it is on the right. Like this lithium ion, it's just floating around in water, not doing anything. It looks the same on the left as on the right, so that's just a spectator. And the same thing is happening with the nitrate. It's the same on the left as on the right. It's just a spectator. And then what's left are things that are changing. The silver is changing, the bromide is changing, it's becoming solid silver bromide. These two ions that were floating around in water come together and precipitate out at the bottom of the beaker as a solid. So you can take a look at the net ionic equation and see very precisely what is changing and what is happening in this reaction. So when you look at these reactions, go ahead and look at the things that are aqueous. Anything else we are not going to separate. Water we are not going to separate because it is not aqueous. It is a liquid itself. So the liquid, water, the water molecules are staying together. Just like the solid silver bromide was staying together, the liquid water is staying together. These are the things that we are separating if they're aqueous. We also look to see if they're ionic, because if it's a covalent molecule, it could be dissolved in water, but it doesn't separate into ions. So it has to be aqueous and ionic. And all three of these are aqueous, and these two you can definitely recognize as ionic. This one, I would have to warn you that it's a strong acid. Strong acid. So it also separates when you put it in water. So then we draw the sodium and the hydroxide ions separately. The oxygen and the hydrogen do not separate from each other. They stay together. That's a polyatomic anion. And then we have hydrogen and chlorine. We have those ions. They're separate from each other. And then on the other side, we have sodium and chloride separate from each other, and the water stays together. Once we have separated everything that needs to be separated, we can cross out the spectator ions. The sodium is not doing anything. It looks the same on the left and the right. The chloride is not doing anything. It looks the same on the left and the right. And then the things that we did not cross out are the things that are changing. So we have hydroxide ion and hydrogen ion coming together to form water molecules, and that is very energetically favorable. That's why when you mix acids and bases, which is what we're doing here, the test tube heats up, and you have to be careful because this is a very strong reaction that happens. OH minus and H plus coming together to make water. The picture of how ionic compounds dissolve in water and how covalent compounds dissolve in water is a link between the total ionic equation and net ionic equation that we're working on in chapter 7, as well as the electrolytes and non-electrolytes and weak electrolytes that we learn about in chapter 9, the beginning of chapter 9. We're not going to spend too much time on calculating the equivalence of charge. That is in the other video that's on the beginning of chapter 9 that goes through 9.1, 9.2, and 9.3. But we'll just not worry about the equivalence of charge too much and just have an idea of the definitions of solubility and what a saturated, supersaturated, and unsaturated solution mean. Also, it's good to keep in mind that the temperature and the gas pressure affect the solubility as well. So when you look through that video that's on the first 3 sections of chapter 9, then just keep those things in mind. One other thing I wanted to point out, a little connection between chapter 9 and chapter 7, is that in chapter 9 we take a look at how water, which is a polar or hydrogen bonded solvent, is better at dissolving ionic and polar compounds. It's not as good at dissolving nonpolar compounds. So most of the time ionic compounds are very well dissolved by water. But back in chapter 7, let's take a look at that. Back in chapter 7, section 4, when we were looking at reactions, one of the reactions is a precipitation reaction. There are certain ionic compounds that bond together too tightly. The cations and anions bond together too tightly, and the water is not able to dissolve them. So there are some ionic compounds that are not soluble in water, and we saw that when we were doing these precipitation reactions here. So I think that we have quite a lot of material to be keeping you busy on this Monday between this short video and the other 2 videos, finishing up chapter 7 and starting chapter 9. I think that is about what we would have done in an in-person lecture today. But I wanted to also point out the next thing for Wednesday that we are going to do. Our in-class worksheet will cover the videos that you're supposed to be watching today. So I think that when we first get into class, we'll try to see if you can do those worksheets, do some problems on your own. So do take a look at those videos. Otherwise, you'll be a little bit lost when it comes to the in-class worksheet. And then we will start off taking a look at section 9.4 with the mass percent concentration. This reminds me a lot of in the beginning of the semester when we were doing density. We would calculate the density, Remember, density is the mass over the volume, and so we spent some time learning how to calculate the density. And then once we did calculate it, we used the density as a conversion factor to convert either grams to milliliters or milliliters to grams. It can convert between mass and volume. We're going to be doing the same thing with concentration. We're going to learn some ways to calculate the concentration, the amount of solute over the amount of solution. So that's that relationship. And then we're going to be using the concentration as a conversion factor to convert between amount of solute and amount of solution. So we'll be looking forward to that on Wednesday, and I will see you then.